Yes. Welcome everyone to today's 1W-MINDS seminar. We're very happy that our speaker today is a former organizer of this seminar, who sort of was part of the team when we initiated this last year. Afonso Bandeira got his bachelor's and master's degree from the University of Coimbra, moved on for a PhD in Princeton, and which he did under the supervision of Amit Singer. After that, went to MIT for a short postdoc, and then as an assistant professor to Courant at NYU, where he was tenured shortly before leaving to become a full professor at ETH in Zurich. I cannot mention all his awards. I just would like to mention two as a representative: the Smale Prize and the Isaac Award. But I think it's also remarkable to mention that he has made a number of contributions to very different areas. You will see today something that sheds lights on some fundamental questions on probability, and which with a lot of applications to data science, and then he has other contributions that really have contributed to specific application areas. So that's really great to have him here today and tell us about matrix concentration and free probability.
Thanks so much, Felix, for such a nice introduction. I hope that the talk lives up to this introduction. So, and I should say, it's been a pleasure to be part of this seminar as an organizer, and now, well, as a speaker, but more even as an audience. While I no longer have to organize and I can enjoy all your hard work and just watch the talks. So I'll tell you today about matrix concentration and free probability. And please, if there's questions, feel free to interrupt. I'm happy to clarify anything. So let me start this by just, let's just briefly describe what is random matrix theory, or where it starts, right? So maybe the classical example is what's called a Vignette matrix. And so this goes back to the 50s, to the work of Vignette. And the idea is the following. Let's say we have a D by D matrix. So a D by D matrix. Okay? And let's say that its entries, say W11, W12, and so on, they're just independent Gaussian. Okay, so Wij is just N01 independent, okay, except that I make it symmetric. Okay, I make doubly symmetric, right? So the top, the top half are independent, and the others get filled up by what they should be. I mean, for the experts in the room, oftentimes you put a little more variance in the diagonal, but I'm gonna sort of put under the rug some of these details that are not core. So now you can ask the question, what does the spectrum, right? So they have this matrix W, right? This D by D matrix. And you can ask the question, what does the spectrum of W look like? Right, so of course the spectrum of W is a random matrix, is a random variable, right? The entries are random, the eigenvalues will be random. But there's this sort of beautiful theorem or a beautiful phenomena that the eigenvalues, if you draw the histogram of the eigenvalues, they'll very quickly, as d goes to infinity. If you try it on the computer, you'll see it with very modest d's. They'll start behaving, or they'll start looking like this so-called semicircular law. So basically, the histogram, the histogram of the eigenvalues, the values of W will start looking, as d goes to infinity, like this beautiful semicircular distribution. Minus 2 root t, 2 root t. Right, and if you look it on the computer, you'll see a few of them here, a few of them here, and so on. And you can state that essentially they weakly converge to this in a certain sense that I don't want to make precise. Moreover, you get all sorts of extra statements about it. People even understand how far two eigenvalues tend to look. If you zoom in, what the distribution is of distances between eigenvalues. You can even argue that no eigenvalue sort of comes out of here. There is nothing here, right? With high probability, there's nothing here. You can show all sorts of statements for these matrices. Okay? And many times in many applications, we need to control eigenvalues of matrices that are formed by either data, by say noise in the process, or by many things. And we need to understand eigenvalues of random matrices. So in many applications, right, so can we understand eigenvalues of random matrices, right, beyond this model? Okay, so maybe you're studying a spectral algorithm, right? And you wanna your algorithm corresponds to computing the leading eigenvector of some matrix, and it has some noise, and you want to know how does the noise on the entries of the matrix affect my algorithm, right? This clearly will tend to be a spectral question, right? In particular, oftentimes when understanding eigenvalues, oftentimes what we want to understand is actually even the spectral norm. Something like the spectral norm of the matrix. Okay, say for example, the maximum eigenvalue, right? Okay, if you understand the minimum eigenvalue, if it has negative eigenvalues, it's usually the same thing. And now we know this for very structured matrices, and there's a whole line of work called the universality that attempts to do this now. If you say, okay, instead of Gaussians, I have another distribution, what can I say? But you still have all this symmetry that it still looks a lot like this Gaussian matrix. But there is another line of work that goes by the name of matrix concentration that attempts to do this. So it attempts to do this for very general models of random matrices. Right? Maybe it doesn't get quite the same level of understanding as we have for Vignette, but it gets a good understanding of the maximum eigenvalue for a large class of matrices. Right? So it deals or handles much larger class of random matrices. Okay. And in particular, one nice way of describing such random matrices is as a sum of independent random matrices. So you take Z1, because you're very used to when we have to control random variables, we write it as a sum of independent of random variables and we control that. So we have Z1 through Zn independent random variables, or random matrices, I should say, right? Random matrices. Right. It tries to study what is the expected value of the sum of these. Right, controls. Okay, so here's a very good example. So example, what's called Matrix Bernstein. I'm assuming some of you have seen this before. So example, Matrix Bernstein. Okay, and for this, you should really see Joel Tropp's monograph. He has a really, really nice monograph in which he develops all of this and many, many of these inequalities. And so just for you to get a flavor of the kind of inequalities that one can write, you say if you take Z1, Zn independent random matrices, so self-adjoint. I mean, it's not important that they're self-adjoint, but I'll sort of in this talk take very much the approach of looking at the simplest possible example to illustrate the kind of things that can be done, but a lot of this is much more general, right? Let's say that they're centered and they're almost surely bounded. Okay. Then Matrix Bernstein says the following: for all t bigger or equal than 0, we have that the probability of the sum of the zk's bigger or equal than t, okay, is smaller or equal than 2d. And then some tail bound that's, for those of you, even if you haven't seen Matrix Bernstein, if you've seen just normal Bernstein inequality, this will be somewhat familiar. It looks just like normal Bernstein. Okay, and the sigma square parameter is, I mean, you'll hear more about it in a second, but it's sort of the right object. It's the expected value of the square of the matrix. Okay, and it's something that's easy to compute. So let me try to convey to you with a personal story how useful this, or illustrate how useful this inequality is. So I think it was back in the fall of 2013. I was a grad student in Princeton, and I was looking at some problems in graphs, and I was studying some relaxations for some inverse problems in graphs. And I was looking in particular at semi-definite programs. And we had come up with a potential dual certificate. And I was trying to show that this dual certificate actually satisfied that it was a dual feasible solution, right? Because these are semi-definite programs, this amounts to controlling the spectrum of this object that you just construct. And I sort of had no idea how to do this, right? Like I knew the stuff about Vignette matrices and so on, but this looked nothing like a Vignette matrix. And then in the fall of 2013, Joel Tropp came and gave a talk in Princeton, and he showed basically this inequality. And I don't know how long, but it was essentially after I saw this inequality, it was immediate. I got exactly, I got the control I needed. Wasn't quite sharp, but it gave me sort of exactly what I needed for to show that this relaxation worked and so on. And since then, I've used this inequality, I think, countless times. So this inequality, however, has a suboptimality. And the suboptimality has to do with this dimensional D factor. Okay? So maybe some of you have used it and have noticed that it not always gives the right answer. And sort of one of the reasons why it doesn't give the right answer is this dependence on the dimension. Okay? And so the goal on this talk is to develop inequalities of this type that don't have this dependency on the dimension. Okay, so this talk, and I'll try to convince you that sort of it's an important question to understand whether this dependency can be removed, and it's connected to the fundamental things in probability theory and free probability and so on. This talk, can this factor be removed? And the real question is, when can it be? And this question was really posed by Joel Tropp in a note, or at least I heard of it, and I think some of you were there. I think Felix was there too. In the spring of 2014, in an Oberwolfach workshop, this question may be formulated essentially this way, or a bit closer to what I'm going to formulate in a second. This was asked explicitly by Joel Tropp, and sort of since then, this has been one of my nemesis problems. I don't know, for now, I guess 7 years. And we finally made some non-trivial progress on it, and let me tell you about it. So before, let me go back to a simpler question. So we will focus on Gaussian matrices. Not necessarily Wigner. They can have very strange dependencies in between them. Like entries can be dependent, they can have different variances, all sorts of things. They're just not, I'm just going to focus in Gaussian matrices. By this, I just mean that the entries of X are jointly Gaussian, and on controlling expected value of X, not the tail. Okay, and let me just say, after this is understood, so after this is understood, one can translate or translate the results to tails of sums of things like sum of ZK for non-Gaussian matrices. But this is not what this talk is about. For those inequalities, I mean, you can see the paper. Okay. Sort of the key question shows up already when we're just dealing with sums of Gaussian matrices. So let me try to convince you of that. So sort of the inequality here is the classical inequality, is the so-called non-commutative Khintchine inequality. Khintchine inequality. Okay, so this is due to Lust-Piquard and Pisier. So it says the following. Okay, so let A1 through AN be self-adjoint. Okay, I'm only dealing with self-adjoint matrices, but there's a classical way to go to general matrices also understand self-adjoint. So that's not really restrictive. It just makes things simpler. Let A1 AN be self-adjoint deterministic matrices, just to make this very clear. Matrices G1 and okay, and G1, Gn IID standard Gaussians. Now the random matrix that we're going to study is the matrix, what's called the Gaussian series of these matrices. Okay, just very briefly, any matrix can be right. Any Gaussian matrix can be written this way, just because any jointly Gaussian vector can be written as sums of independent, like standard right, linear combinations of standard Gaussians with the vector. You just take the spectral decomposition of the covariance, and of course this matrix has jointly Gaussian entries. Moreover, this is, you can have any sorts of dependencies between the entries, any sorts of more variance in some entries than in others. It could be completely inhomogeneous, right? It looks very different than a Vignette matrix. Okay, and now non-commutative Khintchine, what it says the following. Then the expected value of x is smaller or equal than square root log d times sigma. Okay, where sigma is again this parameter. Okay. And this is I think an incredible inequality, because think about it. By doing Jensen on the spectral norm, forget the square for a second, basically expected value of the spectral norm should be bigger than sigma. Up to constants, right? Sigma is like moving the expected value inside, right? And non-commutative Khintchine says that this is always true up to a log factor. Now, this log factor is exactly the same as the D in Matrix Bernstein. Okay, why? Okay, just look at Matrix Bernstein again and see, right? If I want to get right, if this d is to be absorbed by the exponential of minus t square, essentially the t needs to grow by root log d in order to absorb this d. And so basically you get a factor of root log d more on the spectral norm. So this is sort of exactly the same dimensional factor. And the question is when can root log d be removed? So this is the central question. Okay, when is it that non-commutative Khintchine is sharp? Okay, and this was the question that was asked in the Sober-Wolfach workshop in 2014. Now let's look at an example. Okay, so let's look at the Wigner example, right? We just looked at, let's say, so examples, right? Let's get driven by examples, okay, just to see what we expect. So, if X is Wigner, then we know that the spectral norm, right? We know that the eigenvalues of X lie between minus 2 root D and 2 root D, right? So the expected value, and moreover, one can show that, that indeed there's no eigenvalue that goes out, right? I mean, weak convergence by itself wouldn't imply that, but one can show that. Right, then this basically is 2 root d. Okay, however, what is the expected value of x squared? Right, just take x squared, you have this Wigner matrix. Basically, it's a diagonal matrix, because what does entry ij of this square is just the inner product between row I and row j, or column I and column j, right? They're independent. I mean, because there's symmetry, they're not really independent, but every entry that gets hit in the inner product is independent. So there's still inner product 0. And on the diagonal entries, you get the expected value of the L2 norm square of a row, right? Which is exactly D, right? So this is D. Okay, so non-commutative Khintchine would give that the expected value of the norm of x is up to constant smaller or equal than root log d times root d. Right, so it's suboptimal here. Right, there is no d, there is no log. Right, there is really no log, and sort of in the most classical random matrix example, non-commutative Khintchine is giving you the wrong answer. I mean, it's true, of course, but it's not capturing what's going on. Okay, so this was example one. Let's now see an example where the log does show up. And it's a very simple one. Is take x diagonal. Okay, take x. Take x the following way. Take x as, you know, a Gaussian G1, G2, and so on, all the way to Gn. 0, 0, or d, I'm using the language d for the dimension, right, where gk's are just IID 0, 1s. Okay, this is a very simple matrix. Okay, let's compute. So what is, you know, expected value of x squared, spectral norm? So x squared is just the diagonal matrix whose diagonal entries are the square of the Gaussians. Right, so expected, so this is just the identity, and so this is just 1. However, right, okay, so sigma square is 1, right? Now what is actually the expected value of the spectral norm of x? Right, this is the same as the expected value of the maximum of the entries, right? So it's the max over k of gk. But if we have n Gaussians and we take the maximum of them, then this should behave like something like 2 log d. Right, and so in this case, the log is needed. Like log, square root log d is needed. Okay, and non-commutative Khintchine is tight. So the question is, what separates these two examples? And the moral, sort of the idea, you know, or the intuition, and this was already very much present in when Joel Tropp asked this question, is that the Wigners, the diagonal matrix commute and Wigners don't. And this is the key idea. I mean, okay, this is not an idea. This is just, you know, this is just, I guess for now it's not an idea. It's just a statement. Okay, so let me not call an idea because there's no idea here yet. But diagonal matrix and commute and Wigners don't. It's like, I guess, the principle. And the idea is that this is the reason. All matrix concentration statements, most matrix concentration statements, including Matrix Bernstein. So Matrix Bernstein and another and most and related inequalities, they go by saying that they essentially operate by saying that, you know, whatever you want to bound, they go by, right? So they work by showing that commutative case is the worst one. In some form or another. Okay, so they all sort of operate by saying you have your matrices smaller equal than if what would happen if they were to commute. Right. And so in you know, basically Joel in this workshop in 2014 asked, I mean, in a certain way, can non-commutativity be leveraged to improve non-commutative Khintchine, or, you know, or Bernstein, right? If you improve one, you improve the other. Okay, and so this is the question that we answered today. So, you know, I guess I'm roughly halfway. Let me see if I can show you the proof of non-commutative Khintchine. Because for now I gave you two examples, one that commutes, one that doesn't, and I told you, yeah, it's because the log shows up because one commutes and the other doesn't. This is not very convincing because these examples have many other differences between them. Maybe it's because one has n random variables, the other has n square. Like there could be many different things going on, right? So let me show you very quickly a proof of non-commutative Khintchine. Let's see a proof of non-commutative Khintchine. And then you'll see where it's sort of clear that you should be leveraging non-commutativity. So let me show you a proof of non-commutative Khintchine. So there's essentially two simple proofs. They're basically the same. One that you may have seen, especially if you were there in this workshop, is the phased-in integration by parts. I'm going to do one based on Vic's formula. It's basically the same, but this one, what we do next, this makes it more. Makes it easier to see where to like the path that we took. Okay, so the idea is to use moment method. Okay, so you take expected value of trace of x to the 2p, right? Let's remember that x is equal to sum from k from 1 to n of gk ak. Now, I mean, what is this, right? Let's just expand this out to get some sense. Okay, this is, I from 2p from 1 to n. And now you get expected value of the product of the Gaussians. I haven't quite done anything besides just expanding the sum. And of course, I take p to be integer. Otherwise, it'd be hard to interpret this. Okay, now clearly only terms where each Gaussian shows up an even number of times will survive, right? Only terms where gk shows up, say, an even number of times survives, right? If a Gaussian shows up an odd number of times because they're all independent, it's going to be 0. Okay, so there's a very nice way to write this, which is via Vic's formula. I don't have time to prove it or really talk much about it, but it's a formula. And it's in terms of partitions, because every Gaussian is going to show up an even number of times. I'm going to start by partitioning the indices in pairs. Okay, so we take the sum over all possible partitions, or what's called pair partitions. Right? Forget that the Gaussian can show up in 4 places. Let's put that under the rug for now. Okay, but this really is inequality. Okay, so this is the number of pair partitions into P. Now I take all possible choices of indices, right, from these 2P, right? Which Gaussian shows up there, or which index shows up in that product. And what it has is that this choice of indices needs to be compatible with the partition, right? So that the value of f in the partition needs to be the same. Okay, and now it turns out that then I can ignore this expected value with the Gaussians, and I get this. Okay. Okay, so if you're puzzled why 4th moments and 6th moments of Gaussians don't show up, yeah, I don't have time to explain, but this formula is sort of some overcounting and undercounting at the same time, and it happens to exactly match, and it's a nice property of Gaussians. But this is true. So now we use the non-commutative Khintchine Matrix Bernstein type idea, and we say commutative is the worst. Type of thinking, and we say that sort of the worst possible instance for this, right, is sort of small recall in a certain sense. Then when you have just that when the partition, let me put okay, let me be a bit more precise, right? So the worst partition is the one that corresponds to this. So this guy gets connected with this one gets connected to this one gets connected to this one, and so on. Okay, the point is, if the matrix is commuted, then I could reorder them to make every pair show up together. And I'm going to say that this is indeed the worst possible thing. Okay, this is like this commutativity is the worst. I'm not going to prove that, but I'll show you the actual statement. And the statement says the following: that this, for any partition, is smaller or equal in absolute value than exactly this partition I have in blue, right? Where I pick the partition where the first two are together, then the second two are together, and so on. And because each matrix shows up, together, it's basically only the square of the matrix shows up, and so you get trace of sum from k from 1 to p to n, sorry, of ak squared to the p. Right? If I expand this square, all the matrices show up square, so they all show together. It's exactly the same as doing that for the partition, where adjacent things show up are like the partition is things together show up in the same partition. And there's a theorem, this is due to Buchholz, that basically says this is small or equal. So it's even true without any constant, Buchholz from 2001. Okay, so what does this give me? This gives me that this is smaller or equal than the number of partitions times the trace of some k from 1 to n, ak squared to the p. Okay. Okay, so now let's bound each of these things. Okay. So what the number of pair partitions, right, is always of splitting 2p numbers into pairs. Right, I can think, okay, I fixed this the first one, I have to find a friend for it. There's less than 2p options. Then I take this the next one that hasn't been picked. Now there's 2 less options to pick from, and so on. So this is smaller or equal than 2p double factorial. Okay, and this, right, is smaller or equal than d to the sigma to the 2p, right? The spectral norm of sum of ak squares is smaller or equal than sigma squared. So the spectral norm when I take to the p is smaller than sigma to the 2p, and the trace is smaller than dimension over the dimension times the spectral norm. Okay, now what does this give me? Remember, so I'm bounding the expected value of the trace of x to the 2p. So now by Jensen, I can do the following, right? Expected value of x is smaller or equal than 1 over 2p. Expected value trace of x to 2p. But now what is this smaller or equal? This is smaller or equal than 2p, double factorial to the 1 over 2p times d to the sigma to the 2p over 1 over to the 1 over 2p. So I get d to the 1 over 2p, and I get sigma. But now what's the size of this? Right, this basically behaves like p to the p. This is basically a p to the p. Okay, so roughly speaking, this is now smaller or equal. Then we get a p to the p to the 1 over 2p. I get a square root p d to the 1 over 2p sigma. Okay, so now what do I do? Well, I need to make the d go away, right? So I take p to be like log d. And if I take p to be log d, I get a d to the 1 over log d, which is a constant. And I get that the expected value of x is smaller or equal up to constant and square root p, which is log d, times sigma, right? And this is non-commutative Khintchine. So it's proved. Okay. Okay, what went wrong? The only place where something could have gone wrong is in this place where I said that this is the worst possible partition. Nowhere else, anywhere else could anything have gotten wrong. Okay, or at least, okay, it's possible in the very, if you have very special matrices AK, that some of these bounds might be loose, but sort of at the core level, the issue is that we bounded every partition by this one where matrices show up together, right? We use this commutativity is the worst type approach. And the problem in particular is that there are too many, right? There are to many partitions. If there were only like 2 to the p partitions, then we would be okay. Okay, because if there was a 2 to the p, this root p would be like a root 2 and would be okay. So the question is, how do we use this, right? How do we use the fact that maybe most partitions are actually much smaller? And so the idea, right? The idea is that most partitions have a lot of crossings. Okay, what are crossings? Let me draw the partition for you. Crossings would be something where instead of taking the partition like how you did, you take a partition like this. Okay, and of course, I mean, they can be doing whatever they want here. It doesn't matter. And this is a crossing. And maybe partitions with crossings have much smaller value. So maybe when we take this sum, we only care about controlling the partitions that have no crossings. Okay. So if we had a way of doing that, I argue that it would actually be done. Okay, let me just, I mean, this will be a bit fast, but let me just convince you of this. So if we were to sum over just the non-crossing partitions, right? So if we take only the non-crossing partitions of 2p, right? So non-crossing partitions without crossings. Without crossings. These are actually, this correspond to the Catalan numbers. It doesn't matter, but these are actually smaller than 4 to the p. And so what this means, it means if we went back on the proof above, we would get a 4 to the p here, and we wouldn't get a root p here. We would get a constant. And so this log d would disappear. Right? So if partitions with crossings were 0, then everything would disappear. Okay. So let me write that because that's important. If terms in the above proof with crossings were 0, then we would get no log. And this is really the key idea. And so what can you do? You can try to say, provided the matrices commute very little, let me try to bound all these terms. Okay. And so actually, you know, Tropp did try to do this and was able to get a general improvement. So let me try to briefly describe what he did. So in 2015, Tropp introduced a way to control these crossing partitions. So he introduced this matrix alignment parameter. Okay, let me define. You'll see that it's exactly under this motivation of the crossings. Okay, think of the U's as sort of representing everything else that's not in this AI's AJ, right? But it's sort of exactly on this. Okay. And he showed the following inequality. Basically, by bounding, you know, for every crossing term, he was bounding that crossing term using this parameter. Now, not really in this Vix formula way, it was through integration by parts, which actually makes it a bit trickier, but but he was nonetheless able to bound these terms to get an improvement. Okay. We got the following improvement. Okay, so it's an improvement over non-commutative Khintchine. Instead of a root log d gets a log d to the 1/4, and now the log d goes into the other parameter. So this already captures like this key idea that crossing should correspond to cancellations. This has two issues. One issue is that this is still not the right term, right? Still, still a dimensional dependency. Right, it's just smaller. In particular, not the right answer for Vignette, which is sort of the simplest matrix, when the matrix example. And another issue is that WX seems very difficult to compute. WX has this, it's nicely motivated by the crossings, but because of these max over the unitaries, right? Because of this max of the unitaries, essentially, I don't know how to compute this in any example. I mean, except very specific ones. And so we take a different approach. Okay, so what we did now. So we do the following. Okay, so EBVH 21. What do we do? We dream of a model where crossings don't exist. Okay, what if our model was such that crossings, terms with crossings don't matter? Don't matter, or like are small or are zero, right? I'm not being so specific for now. Okay, so I'm going to dream of another model. Instead of having x equals sum of gk ak, I'm going to take the following model. I'm going to take xn. This is just an index. It's not. I'm not taking any powers. Equals to gn tensor ak, where gkn, R is a Vignette matrix, or I should say, are independent Vignette matrices. Not sure what this is, but independent Vignette matrices. This is a different matrix, but now I've created non-commutativity very strongly. Okay. In particular, if now I go back to the proof, right? Now let's study this object instead. You don't know how to say something about your matrix. Let's dream of a simpler matrix, or I mean, doesn't look any simpler, but one for which this phenomena of there being no crossings is very apparent. If we were to carry out this proof, right, what we would see, instead of taking expected value of the product of the G's, we'd basically get something like expected value of trace of the product of the Vignettes. And now, because the Vignettes themselves, we know that they're very, very non-commutative. Every time we see a crossing, this should tend to 0. And there's ways to make this precise. Okay, and I'll describe this in a second. Okay. And so for this matrix, it is indeed true that the crossings don't matter. Okay, for enlarge, or I should say, okay, to be more precise, as n goes to infinity, the terms with crossings go to 0. Okay. And I want to just at least be intuitively, for this to be, yeah, intuitively believable at least, right? If you were to expand this out with the Vigners, basically, instead of getting this expected value of the product of GKs, you would get expected value of the product of Vigners. And this would be 0 unless the Vigners, unless there were no crossings. This model is the model in the limit that corresponds to a Vick's formula where you sum only over non-crossing partitions. Okay. So when it goes to infinity, as n goes to infinity, this is the model where instead of having Vick's formula over any partitions, you have Vick's formula only over crossing partitions. So if you want to study, we want to study this object here. We don't know quite how to do it. And this business of trying to bound terms seems very difficult, right? I mean, after a lot of effort, it gives this improvement that, it still doesn't give the right answer for Vignette matrices. But what if we change the matrix, right? What if we make the matrix so that when we write Vick's formula, the crossing terms go away? Okay. And the point, the key idea of why this is true and why you can compute with this is due to free probability. So free probability allows us to compute, study this object, this random matrix, as n goes to infinity. Right, and there's a limiting object, right? The limiting object, and I don't want to say much about it. Object is so-called what we call x-free, okay? And it's basically the following. Okay, where these guys are called the independent semicircular families or freely independent semicircular family. Okay, so it doesn't really matter what this is exactly, the sum operator in infinite dimensions. What matters is that I'm changing the model to a model where crossings completely disappear because I changed the matrix. This is not the same random matrix. Free probability allows us to make computations about these objects in the limit. There's a very nice limiting object. Think of it as the Gaussian in this world. The semicircular families are like the Gaussian in this world, and we can do all these calculations. And in particular, it's very easy to get things like, norm of x-free is smaller or equal than 2 sigma and all sorts of statements without any kind of, relatively easy to get things like this, right? And you see why, because if you were to do Vick's formula, there would be no crossings. So for this ideal dreamed up object, we know how to carry our program exactly, right? Because we made an object so that the object has no crossings. It's sort of maximally non-commutative. Okay, and so the idea now for the proof, okay, is to interpolate between x and xn. Okay, so Gaussian interpolation, right? And show that if a certain parameter Vx, that I'll describe in a second. Okay, maybe I'll just give you the definition right now. Is the covariance, and I'll say a few words about it. It's small, then the derivative along of this interpolation is very small. Then x, let me put it in between parentheses, in between the quotes, x behaves like x-free. And in particular, we immediately get statements of the following type, inequality right away. Expected value of x is smaller or equal than 2 sigma. Not only you get the constant, but you get the right constant. Like 2 is the right constant for Vignette. 2 sigma plus a constant times Vx times log d to the 3/2. Vx is easy to compute. I should make right? You take your matrix X, you look at its covariance, and you just take the spectral norm of that, d squared by d squared covariance. Okay, it gives the right answer in a range of examples, including Wigner. I mean, in Wigner, this, sigma will be like root d, and the covariance is just the identity. So this is like 1, right? So it's giving the right answer in a very strong way, right? It's just, this would be of order root d, and this would be of order 1, right? So you can even be a lot less random than Wigner and still be okay, right? I say in many examples. It recovers these things that we knew about independent entries, even if very inhomogeneous. It is able to study things like pattern matrices, glued entries, Gaussians in subspaces, many, many examples. This gives the right answer. And let me just make a few points before I finish. It's much more general than this, in a sense that many times the bound is better. The bound is better than 2 root sigma sometimes. Okay? Really, what the bound says is the bound is given in terms, right? It's really something like in terms of this x free plus and then the other terms. And sometimes x free is smaller than 2 root sigma. And this is something that can be computed. It's sort of between sigma and 2 sigma. Sometimes it's better than 2 sigma. Okay. You get something about the whole spectrum. You get actually that the spectrum of X is inside the spectrum of X free. So plus or minus epsilon, where epsilon depends on that covariance parameter. Right. So if you then apply interpolation not to traces of X to 2P, but resolvents and things like this, you get information in the if X free had a gap on its spectrum, X will also have a gap on its spectrum. So you get information about the whole spectrum. And you get what's called a stronger symptotic freeness. I mean, this is only for the experts. But stronger symptotic freeness basically tells you that, these matrices, if you take independent copies of a matrix that satisfies, for which Vx is much smaller than sigma, then they in the limit behave just like semicircular families. Okay. And even for Wigner, this was a big achievement to prove this some years ago. And with this tool, you can do it for essentially any of these matrices with very, very little structure on the matrices. Okay, so I mean, I could give you some examples, but you can look in the paper. If you have independent entries, but very, very different variances, if you have, say, you force entries in a very deterministic way to be equal to others, right? This might show up if you're looking at dual certificates of sum of squares and so on. This inequality will improve over Bernstein in a long range of examples. And of course, it gives a matrix, it implies a matrix concentration inequality for sums of ZKs. You can let me write X equals this, non-Gaussian. So for this, I'll refer to the paper. See the paper. Yeah, but basically you can use comparison between non-Gaussian Gaussian and get some form of either symmetrization, universality, something like this. Okay, I mean I'll stop here. I don't want to take any more time, and I want to leave time for questions. Yeah, I'm very happy to answer any questions. Thank you.
Yes, thanks a lot for this very exciting talk. Are there questions? Please feel free to unmute yourself and ask.